Hello there and welcome back to Sleepy Tin Foil Hat. Tonight, we're going to drift far beyond the familiar edges of the world and into a place that feels almost untouched by time. A place where the air itself carries history, where the ground beneath your feet is not really ground at all, but miles of compressed memory. Antarctica is often described as empty, but that word doesn't quite fit. It is not empty, it is hidden. Beneath its vast white surface lies a continent that has recorded millions of years of Earth's story, layer by layer, frozen into silence. When you look at Antarctica, you are not just looking at ice. You are looking at time preserved, at processes slowed down to a pace that feels almost unreal. And the deeper you go, the more that quiet surface begins to feel like a cover, rather than a conclusion. If you enjoy these kinds of slow, late-night journeys into the unknown, I'd really appreciate it if you took a moment to subscribe and maybe leave a comment telling me where you're listening from tonight. I always like seeing how far these ideas travel, and it helps more people find their way here, one curious mind at a time. But for now, there's nothing you need to do. Just settle in, let your breathing slow, and follow along as we begin to uncover what might be one of the most quietly mysterious places on Earth. Antarctica exists in a strange position within human understanding. It is one of the largest landmasses on the planet, yet it has no permanent population, no cities, and no long-standing human history in the way other continents do. Its governance is equally unusual. Under the Antarctic Treaty, the continent is designated for peaceful purposes and scientific research. Military activity is prohibited, resource extraction is heavily restricted, and territorial claims are essentially held in suspension. On paper, this makes Antarctica a symbol of international cooperation. But when you look at it more closely, it also creates an environment where access is limited, where large areas remain unexamined, and where the majority of what exists there is known only through indirect measurement. The ice sheet that covers Antarctica is not just a surface feature. It is a structure of immense scale, averaging over a mile in thickness and reaching depths of nearly 3 miles in some regions. This ice did not form quickly. It accumulated over hundreds of thousands, in some areas millions of years, compressing snowfall into dense layers that trap within them microscopic particles, gases, and chemical signatures from past eras. Scientists drill deep into this ice to extract cores that function almost like timelines. Each layer represents a different period, and by analyzing the trapped air bubbles, researchers can reconstruct atmospheric conditions going back hundreds of thousands of years. This is how we know that Antarctica was not always frozen. Geological and fossil evidence suggests that it once supported forests, with temperatures far warmer than anything seen there today. That transformation alone raises significant questions. A continent that is now one of the coldest places on Earth once supported complex ecosystems. Trees, plant life, and possibly even animal species existed where now there is only ice. The shift from that environment to the current frozen state was not instantaneous. It was the result of long-term climatic changes, continental drift, and shifts in ocean circulation. But what makes Antarctica particularly compelling is that much of that earlier world is still there, preserved beneath the ice. Unlike other continents, where erosion, vegetation, and human activity have reshaped the surface, Antarctica has effectively sealed its past under layers of frozen material. In theory, large portions of its geological and possibly even biological history remain intact, waiting to be uncovered. Beneath that ice, the continent is far from static. There are mountain ranges, valleys, and even active geological processes. One of the most well-known subglacial features is Lake Vostok, a vast body of liquid water buried beneath more than 2 miles of ice. The existence of such lakes was initially surprising, But it is now understood that geothermal heat from the Earth's interior, combined with the insulating properties of the ice above, can maintain liquid water in these extreme conditions. What makes Lake Vostok particularly significant is its isolation. It has likely been cut off from the surface for millions of years, creating an environment that has evolved independently from the rest of the planet. When scientists first reached this lake through drilling, they approached it with extreme caution. Contamination was a major concern, as introducing modern microorganisms could disrupt whatever ecosystem might exist within. Samples taken from the ice just above the lake revealed microbial life, organisms capable of surviving in complete darkness, under immense pressure, and at temperatures close to freezing. These extremophiles challenge conventional assumptions about the limits of life. If life can persist in such conditions on Earth, it suggests that similar environments elsewhere in the solar system, such as the subsurface oceans of icy moons, could also support life. But Antarctica's mysteries are not limited to what has been formally studied. The continent has also become a focal point for speculation, particularly in relation to satellite imagery and remote sensing data. Over the years, there have been claims of unusual geometric formations visible beneath the ice or on its surface. Some interpret these as natural features, ice formations shaped by wind and temperature gradients, or rock structures partially exposed through melting. Others suggest that some of these patterns appear too regular, too structured, to be entirely natural. While most of these claims remain unverified and are often explained through conventional geological processes, their persistence reflects a broader reality. Antarctica is one of the few places on Earth where large-scale features can exist largely unexamined. Access plays a significant role in this. Much of Antarctica is extremely difficult to reach, and even scientific expeditions are limited to specific regions. There are areas where flights are restricted, where data is sparse, and where environmental conditions make sustained observation nearly impossible. From a scientific standpoint, this is understandable. The continent is fragile, and human activity must be carefully managed to prevent long-term damage. But from an analytical perspective, it also means that our understanding of Antarctica is incomplete. We rely heavily on satellite data, indirect measurements, and limited field studies. There are gaps in the data, and where gaps exist, interpretation becomes more complex. Another factor that contributes to Antarctica's enigmatic nature is its acoustic environment. It is often described as one of the quietest places on Earth, but this quiet is not absolute. It is characterized by the absence of typical human-generated noise. Instead, the sounds that do exist, wind moving across the ice, distant cracking from shifting glaciers, the subtle vibrations of the ice sheet itself, become more noticeable. Researchers have recorded low-frequency sounds beneath the ice, generated by movement within the glacier or by interactions between ice and underlying rock. These signals are still being studied, but they add another layer to the continent's complexity. Antarctica is not silent. It simply operates on frequencies and timescales that are easy to overlook. When you begin to consider all of these elements together, the preserved history within the ice, the hidden lakes, the limited access, the unusual data patterns, it becomes clear that Antarctica is less understood than its size would suggest. It is a continent that holds vast amounts of information about Earth's past, present, and possibly even its future. At the same time, it is a place where complete knowledge remains just out of reach, where each discovery tends to raise as many questions as it answers. And that may be what makes Antarctica so compelling. Not just what we know about it, but what we don't. The idea that beneath those miles of ice, there are still systems, structures, and histories that have yet to be fully explored. That even now, in a world mapped and measured to an extraordinary degree, there are still places where uncertainty remains. As we continue, we'll move deeper into those uncertainties. into the signals detected beneath the ice, the anomalies recorded by instruments, and the theories, some grounded, some more speculative, that attempt to explain them. Because Antarctica is not just a frozen landscape, it is an active field of study, a repository of ancient data, and possibly a place where some of the most interesting questions about our planet are still waiting to be answered. As we move further into Antarctica, the surface begins to feel less like a boundary and more like a barrier, because what appears stable from above is, in reality, constantly shifting. The Antarctic ice sheet is not a solid, unmoving mass. It flows, slowly, almost imperceptibly, but continuously. Entire sections of ice behave like a viscous fluid, spreading outward from the interior toward the coastline. This movement is driven by gravity and pressure, with ice deforming under its own immense weight. In some regions, this flow feeds massive glaciers that extend hundreds of kilometers, eventually breaking off into the ocean as icebergs. But what makes this system particularly interesting is not just the movement itself, but what it reveals underneath. As ice flows, it interacts with the bedrock below, eroding, polishing, and in some cases exposing features that have been hidden for millions of years. Radar imaging, capable of penetrating deep into the ice, has revealed entire mountain ranges buried beneath the surface. One of the most notable is the Gamburtsev subglacial mountains, a range comparable in scale to the European Alps, completely concealed beneath kilometers of ice. What makes this discovery unusual is not just the size of the mountains, but their apparent preservation. They show sharp peaks and deep valleys, features that would typically be eroded over time, yet here they remain relatively intact, protected by the ice above. This raises an important point about Antarctica. In most parts of the world, geological processes like erosion, vegetation growth, and human activity continuously reshape the landscape. But in Antarctica, the ice acts as a kind of protective layer, preserving underlying features in a state that can remain unchanged for extraordinarily long periods. It creates conditions where ancient structures, whether geological or otherwise, could, in theory, remain hidden and intact far longer than they would anywhere else on Earth. And this is where speculation begins to intersect with observation. Because when scientists analyze radar data and satellite imagery, they sometimes encounter anomalies, not necessarily in the sense of something artificial, but in the sense of patterns or formations that are not immediately easy to categorize. Subglacial lakes, for example, were once considered anomalies until they became accepted as part of the Antarctic system. The same is true for certain radar reflections that suggest voids, channels, or unusual density variations beneath the ice. There are now over 400 known subglacial lakes across Antarctica, forming a network of isolated water bodies connected in ways that are still being mapped. These lakes do not exist independently. Some appear to be linked by subglacial waterways, allowing water to move beneath the ice sheet over long distances. This creates a dynamic hydrological system hidden entirely from view, one that influences how the ice above behaves. In some cases, the sudden movement of water beneath the ice can accelerate glacier flow, acting almost like a lubricant between the ice and the bedrock. This system introduces a level of complexity that challenges earlier assumptions about Antarctica being static and unchanging. Instead, it is a layered system, ice above, water beneath, rock below that, each interacting with the others in ways that are still not fully understood. And within that complexity, there are signals. In 2018, a high-energy particle detection event over Antarctica drew significant attention from the scientific community. Instruments designed to detect neutrinos, extremely low-mass particles that rarely interact with matter, recorded signals that appeared to be coming from below the ice rather than from above. This was unexpected. According to current models, such particles should not be able to pass through the entire Earth and emerge in the way that was observed. The event, associated with experiments like those conducted by NASA and other research groups, led to multiple hypotheses, including the possibility of unknown particle interactions or previously unobserved physical processes. While most scientists lean toward conventional explanations, instrumental anomalies, rare interaction pathways, or gaps in current models, the event remains a point of interest. It highlights how Antarctica, due to its unique conditions, often becomes a testing ground for phenomena that are difficult to observe elsewhere. The thick ice provides a stable, low-noise environment, ideal for detecting subtle signals, whether they originate from space or from within the Earth itself. But not all signals are as easily categorized. There have been reports of low-frequency acoustic anomalies detected beneath the ice, sometimes described as rhythmic or patterned. In many cases, these can be explained by natural processes, ice shifting, cracking, or interacting with underlying water. However, the consistency and structure of some recordings have led researchers to examine them more closely. Ice, under pressure, can produce a wide range of acoustic signatures, and when those signals travel through vast, dense layers, they can appear more organized than they actually are. Still, the idea that Antarctica might be generating signals, whether geological, hydrological, or otherwise, adds another dimension to its study. It is not just a place to observe static features, but a system that produces data continuously, much of it still being interpreted. Then there is the question of what lies deeper. Beyond the lakes, beyond the bedrock, Antarctica sits atop a complex geological foundation. Parts of the continent are believed to be remnants of ancient supercontinents, including Gondwana. This means that the rocks beneath the ice could contain records of some of the earliest chapters of Earth's geological history. In certain regions, there are indications of volcanic activity, including subglacial volcanoes that remain largely unstudied due to their inaccessibility. Volcanic heat could play a role in maintaining liquid water beneath the ice, contributing to the formation of subglacial lakes and influencing ice flow patterns. It also raises the possibility that some areas of Antarctica are more geologically active than previously assumed. If heat sources exist beneath the ice, they could create localized environments that differ significantly from the surrounding frozen landscape. And once again, this brings us back to a recurring theme. Antarctica is not fully mapped, not in the way other continents are. Large portions of its subsurface remain inferred rather than directly observed. We rely on indirect methods, radar, seismic imaging, satellite data, to build models of what lies beneath. These models are increasingly detailed, but they are still models. They are interpretations based on available data, and like all interpretations, they are subject to revision as new information becomes available. This leaves room for both discovery and uncertainty. And in that space between what is known and what is not, theories begin to form. Some are grounded firmly in science, exploring how subglacial ecosystems function, how ice dynamics respond to climate change, or how geological processes operate beneath extreme pressure. Others move further into speculation, questioning whether all observed anomalies can be explained by current models, or whether there are aspects of Antarctica that remain outside conventional understanding. What is clear is that Antarctica continues to produce data that challenges assumptions. It forces researchers to adapt their models, to consider new variables, and to remain open to the possibility that the continent operates in ways that are not immediately obvious. And as we continue, we'll look more closely at some of those theories. The interpretations of unusual structures, the historical expeditions that reported unexpected findings, and the ongoing debate about how much of Antarctica's story has actually been uncovered. Because the deeper you go, beneath the ice, beneath the data, the more it begins to feel like Antarctica is not just preserving the past, it may also be shaping the questions we ask about the future. As we continue moving deeper into Antarctica's layered system, it becomes increasingly clear that the continent is not just a passive archive of Earth's past, but an active participant in planetary processes that extend far beyond its borders. One of the most significant of these processes is its influence on global ocean circulation. Surrounding Antarctica is the Antarctic Circumpolar Current, the strongest ocean current on Earth. It flows uninterrupted around the continent, connecting the Atlantic, Pacific, and Indian Oceans, effectively acting as a global conveyor belt. This current regulates heat distribution across the planet, and any change in its behavior can have far-reaching climatic consequences. What makes this particularly interesting is how closely this system is tied to the ice itself. As Antarctic ice melts, even at relatively small rates compared to its total mass, it introduces fresh water into the surrounding ocean. This alters the salinity and density of seawater, which in turn affects how ocean currents move. Scientists have been monitoring subtle changes in this balance, noting that shifts in Antarctic ice dynamics could influence weather patterns thousands of kilometers away. In that sense, Antarctica is not isolated at all. It is deeply connected to the rest of the Earth, acting as a kind of regulator that helps maintain global equilibrium. But beneath this large-scale system, there are smaller, more localized processes that are equally compelling. One of the more unusual discoveries in recent years involves fast-moving rivers of ice, known as ice streams. Unlike the surrounding ice sheet, which moves slowly, these streams can flow at speeds of several hundred meters per year. They are essentially channels within the ice, guided by conditions at the base, often influenced by the presence of subglacial water. What's particularly intriguing is that these ice streams can start and stop over time, sometimes shifting their paths entirely. The mechanisms behind these changes are still being studied, but they suggest a level of internal variability that is not immediately visible from the surface. This variability becomes even more complex when we consider the interaction between ice and the underlying geology. Seismic studies have shown that parts of Antarctica experience low levels of tectonic activity. While not comparable to major earthquake zones, these movements can still influence how ice behaves above. Small shifts in the bedrock can alter pressure distributions, potentially triggering changes in ice flow or even affecting subglacial water systems. And then there are the signals that don't fit neatly into these models. Over the years, various research teams have reported detecting electromagnetic anomalies in certain regions of Antarctica. These are not necessarily strong or consistent signals, but they are unusual enough to warrant investigation. In many cases, they can be attributed to variations in the Earth's magnetic field, interactions with solar radiation, or localized geological features such as mineral deposits. However, the fact that these anomalies are often detected in areas with limited direct exploration adds another layer of uncertainty. One area that has drawn particular attention is near the Ellsworth Mountains, where radar and satellite data have revealed complex subglacial topography. Some formations appear highly symmetrical, leading to speculation about their origin. Most geologists argue that these shapes can be explained through natural processes, glacial erosion, tectonic uplift, and sediment deposition over long periods. But the precision of some features has led others to question whether all observed structures are purely geological. This is where Antarctica becomes a kind of intersection between data and interpretation, because the data itself is often incomplete. Radar imaging, while powerful, has limitations. It can indicate the presence of structures, but not always their exact composition. Seismic data can reveal density differences, but not necessarily the full context of what those differences represent. As a result, scientists build models, best fit explanations based on available evidence. These models are constantly refined, but they are still interpretations. And when interpretations are involved, alternative theories tend to emerge. Some of these theories focus on the idea that Antarctica may have once been home to advanced prehistoric ecosystems, far more complex than previously understood. This is not entirely outside the realm of scientific discussion. There is evidence that Antarctica was once part of a much warmer global system, and that it supported diverse life forms. Fossils of plants and microorganisms have already confirmed this. The question is not whether life existed there, it clearly did, but how extensive and complex that life might have been. More speculative ideas go further, suggesting the possibility of structures or formations that predate known human history. These ideas often draw from satellite imagery or interpretations of subglacial features. While mainstream science remains cautious, emphasizing natural explanations, the lack of direct access to many regions means that some questions remain open. At the same time, Antarctica has a documented history of exploration that includes its own set of anomalies. Early expeditions, particularly during the early 20th century, often reported unusual conditions, optical illusions caused by the atmosphere, magnetic compass irregularities, and extreme environmental phenomena that were not fully understood at the time. The continent's atmosphere can create mirage effects, bending light in ways that make distant objects appear distorted or displaced. This has led to historical accounts of sightings that later proved difficult to verify. One of the most well-known early explorers, Roald Amundsen, successfully reached the South Pole in 1911. His expedition, like others of that era, highlighted just how unpredictable and extreme Antarctica can be. Equipment behaved differently, navigation was challenging, and environmental conditions could shift rapidly. While modern technology has improved our ability to operate in such environments, many of these challenges remain. And that brings us to a key point. Even with satellites, advanced sensors, and decades of research, Antarctica is still not fully understood. There are regions that have been mapped only in broad terms, areas where direct sampling has never occurred, and systems that are still being modeled rather than directly observed. This creates a unique situation. Unlike most other places on Earth, where data is dense and continuously updated, Antarctica still contains gaps, areas where our knowledge is limited. And in those gaps, both scientific inquiry and speculation continue to expand. As we move forward, we'll begin to look at some of the more persistent theories associated with Antarctica. The idea of hidden structures, the interpretation of unusual satellite data, and the question of whether all observed anomalies can be explained within current scientific frameworks. Because Antarctica, more than almost any other place on Earth, sits at the edge of what we know, and what we are still trying to understand. As we move further into the deeper layers of Antarctica's mystery, the focus begins to shift from what has been observed to how those observations are interpreted. Because one of the most important aspects of Antarctica is not just the data itself, but the limitations surrounding that data. Unlike other continents, where direct exploration is relatively straightforward, much of Antarctica must be studied indirectly. Radar pulses, satellite imaging, gravitational mapping. These are the tools that allow us to see beneath the ice. But each of these methods comes with constraints: resolution limits, signal distortion, interference from the ice itself, and when you're working with incomplete pictures, even small anomalies can stand out. One of the more discussed examples involves structures detected through satellite radar that appear to have unusually sharp angles or symmetrical outlines. These features are often located beneath thick ice layers, making direct verification nearly impossible without extensive drilling operations. In many cases, scientists interpret these shapes as the result of natural geological processes, fault lines, fractured bedrock, or erosional patterns shaped over millions of years. But there are instances where the geometry appears unusually precise. Now, precision in nature is not unheard of. crystals form with symmetry. Volcanic columns can create near-perfect hexagonal patterns. But when symmetry appears on a larger scale, particularly beneath a continent-sized ice sheet, it naturally draws attention. Some of these formations have been loosely compared to pyramidal shapes, although such comparisons are often exaggerated outside of scientific circles. Still, the underlying question remains: how much of what we're seeing is fully understood, and how much is simply interpreted based on the closest available explanation? This question becomes more relevant when we consider how Antarctica is monitored. Much of the continent is observed through satellites operated by organizations like NASA and the European Space Agency. These satellites collect enormous amounts of data: topography, ice thickness, temperature variations, gravitational anomalies. But raw data is not the same as direct observation. It must be processed, filtered, and interpreted. And during that process, subtle patterns can emerge that were not the original focus of the study. For example, gravitational mapping has revealed areas where the density beneath the ice differs significantly from surrounding regions. These anomalies are typically explained by variations in rock composition or subglacial water systems. But in some cases, the boundaries of these anomalies appear sharply defined, almost as if separating distinct regions. Again, there are scientific explanations for this: tectonic boundaries, sediment deposits. But the clarity of some of these divisions continues to be studied. Then there is the question of mapping accuracy itself. Antarctica's remoteness means that high-resolution mapping is not uniform across the continent. Some regions have been studied extensively, while others remain mapped only at a coarse level. This uneven coverage can create the illusion of anomalies simply because one area has more detailed data than another. But it also means that certain features may remain undetected until technology improves or new surveys are conducted. And occasionally, when new data does come in, it changes the picture. There have been cases where updated radar scans revealed subglacial features that were not visible in earlier datasets. Entire valleys, previously unknown, have been identified beneath the ice. In one instance, researchers discovered a massive canyon system stretching for hundreds of kilometers, comparable in scale to some of the largest canyons on Earth. These discoveries highlight just how much of Antarctica remains hidden, even with modern technology. But beyond the geological, there are also patterns in how Antarctica is accessed and studied. Certain regions are designated as specially protected areas under international agreements. These designations are primarily intended to preserve fragile ecosystems and ensure that scientific research can continue without interference. However, they also limit access. Not all researchers can enter these zones freely, and data collected within them is often controlled by specific programs or institutions. From a scientific standpoint, this is standard practice. Sensitive environments require careful management, but from an analytical perspective, it creates a structure where information is not always evenly distributed. Some findings are widely published. Others remain within specialized research circles, and this uneven flow of information can contribute to the perception that Antarctica holds more than what is openly discussed. Another layer to consider is communication. Research stations across Antarctica operate in extreme conditions, often isolated for months at a time. Data transmission relies on satellite links, which can be limited by bandwidth and environmental interference. This means that not all observations are immediately shared in real time. Some data is stored, processed later, and only then integrated into broader scientific analysis. And within that delay, there is space. Space for interpretation. Space for speculation. Because when information is not immediate, the absence itself becomes noticeable. There have also been historical periods where Antarctica attracted attention beyond purely scientific interest. During the mid-20th century, for example, Several large-scale expeditions were conducted under the context of geopolitical tension. One of the most well-known was Operation High Jump, a US Navy mission that deployed thousands of personnel and extensive equipment to the continent shortly after World War II. Officially, the operation was described as a training exercise and a test of equipment in polar conditions. But the scale of the mission and the fact that it ended earlier than planned has led to ongoing speculation about its true objectives. Some theories suggest that the expedition encountered unexpected conditions or findings, although no concrete evidence supports these claims. Still, the event remains a point of reference in discussions about Antarctica's less documented history. And that pattern continues. Large-scale operations, limited access, indirect observation, and occasional anomalies in data. All of these elements combine to create a landscape that feels only partially revealed. But what's important is to maintain perspective. Science operates through evidence, through repeatable observation, through models that can be tested and refined. Most anomalies, when studied closely, do find explanations within existing frameworks. But the process of reaching those explanations is ongoing. It evolves as new data becomes available. And Antarctica, perhaps more than any other place on Earth, ensures that process never truly stops, because it continues to present new variables, new signals, new structures beneath the ice, and each one invites the same quiet question. Is this something we already understand, or something we are only beginning to see? As we continue, we'll begin to explore some of the more persistent narratives tied to Antarctica. The idea of ancient civilizations, the interpretation of satellite imagery in alternative contexts, and how these theories intersect with actual scientific findings. Because sometimes, the boundary between observation and speculation is not as clear as it first appears. As we move further into the more speculative layers surrounding Antarctica, it becomes necessary to separate two parallel tracks that often overlap. On one side, there is the scientific framework, data, measurements, repeatable observations. On the other, there is interpretation shaped by incomplete information, historical context, and human tendency to search for patterns. Antarctica sits directly between these two, which is why it appears so frequently in discussions that extend beyond conventional science. One of the most persistent ideas is that Antarctica may have been ice-free far more recently than traditionally assumed. Mainstream geology places the major glaciation of Antarctica beginning around 34 million years ago. However, there is evidence suggesting that certain regions may have experienced periods of partial melting or reduced ice coverage much later than that. Sediment cores extracted from the ocean floor near Antarctica contain materials that indicate episodic warming events, during which ice sheets retreated and exposed land surfaces. This has led to a more nuanced understanding. Antarctica was not simply frozen once and left unchanged. It has undergone cycles, advancing ice, retreating ice, shifting climate conditions over vast timescales. And within those cycles, there are windows of possibility. Periods where parts of the continent may have been accessible, where ecosystems could have re-emerged, where geological features now buried under ice may have been exposed for extended durations. From a strictly scientific standpoint, these windows are still placed far outside human history. But the existence of these cycles opens the door, at least conceptually, to questions about what those exposed landscapes might have looked like, and what evidence they might still hold beneath the ice today. This is where alternative interpretations begin to take shape. Some theories suggest that if Antarctica had regions free of ice at certain points, those regions could have been mapped or even visited by early civilizations. One of the most frequently cited references in this context is the Piri Reis map. Created in 1513, this map appears to show a southern landmass that some interpret as Antarctica without ice coverage. Mainstream historians and cartographers generally explain this as a misinterpretation of South American coastlines, combined with the mapping limitations of the time. The projection methods used in early cartography often distorted landmasses, especially in the southern hemisphere. However, the map continues to be discussed because of how closely some sections seem to align with the general shape of Antarctica's coastline beneath the ice. The key point here is not whether the map definitively represents Antarctica, but why such interpretations persist. It reflects the broader idea that Antarctica, due to its hidden nature, allows for multiple readings of the same data. Another area where this dual interpretation appears is in satellite imagery. High-resolution images of Antarctica have revealed formations that, at first glance, appear structured: sharp ridges, triangular peaks, and linear alignments. These are often highlighted in discussions about hidden structures beneath the ice. In most cases, geologists attribute these shapes to natural processes. Glacial erosion can produce surprisingly regular patterns, and when combined with lighting conditions and shadow angles, these features can appear more geometric than they actually are. However, what keeps the discussion active is the scale and isolation of these features. If a similar formation were found in a well-studied region, it would likely be investigated directly and classified quickly. In Antarctica, direct investigation is often not feasible. So the interpretation remains based on imagery alone. And imagery, by its nature, leaves room for perspective. There is also the question of subglacial voids, areas beneath the ice where radar suggests lower density or open space. These are typically explained as water-filled cavities, sediment pockets, or variations in bedrock composition. But in some cases, the boundaries of these voids appear unusually defined. Again, the scientific explanation focuses on natural processes, but the consistency of certain patterns has led to continued examination, particularly as radar technology improves and provides more detailed scans. At the same time, Antarctica's role in global monitoring has expanded significantly. Research stations across the continent are equipped with instruments that measure atmospheric composition, seismic activity, and cosmic radiation. These stations contribute to a wide range of scientific fields, from climate science to astrophysics. The continent's low levels of electromagnetic interference make it an ideal location for detecting signals that would be difficult to isolate elsewhere. This includes experiments related to cosmic background radiation, neutrino detection, and even the study of gravitational waves. Facilities such as those operated in collaboration with organizations like National Science Foundation have turned Antarctica into a key site for observing phenomena that originate far beyond the Earth. And this introduces another layer, because Antarctica is not just a place where we look down, into the ice, into the past, but also a place where we look outward, into space. This dual perspective, downward into Earth's history and outward into the universe, creates a unique environment where multiple fields of study intersect, and where different types of anomalies can appear. Some of these anomalies are eventually explained, others remain open questions, but the pattern is consistent. Antarctica produces data that challenges assumptions, and when assumptions are challenged, theories expand. Some remain within scientific boundaries, exploring new models of ice dynamics, subglacial ecosystems, or atmospheric behavior. Others extend further, suggesting connections that are not yet supported by direct evidence, but are still considered in broader discussions. What's important is that Antarctica continues to be a place where discovery is ongoing, not in the sense of sudden, dramatic revelations, but in the gradual accumulation of information that reshapes how we understand the continent over time. And as that understanding evolves, so does the line between what is considered known and what remains uncertain. Because even now, with satellites mapping its surface and instruments probing its depths, Antarctica is not fully revealed. It is still, in many ways, an unfinished map. And as we continue, we'll begin to explore some of the more unusual environmental phenomena reported in Antarctica: optical effects, atmospheric distortions, and the ways in which extreme conditions can alter perception itself. Because sometimes, what is observed is not just a reflection of what exists, but also of how we see it. As we continue deeper into Antarctica's layered complexity, the focus begins to shift from what exists beneath the ice to how the environment itself can influence what is seen, measured, and even believed. Because Antarctica is not just physically extreme, it is perceptually extreme. The conditions there can distort distance, alter sound, bend light, and in some cases, create observations that feel almost disconnected from normal experience. One of the most well-documented phenomena is the optical effect known as a superior mirage. In Antarctica's atmosphere, layers of air at different temperatures can refract light in unusual ways, bending it over long distances. This can cause objects beyond the horizon to appear elevated, stretched, or even duplicated. Entire landforms can seem to float above the ice, inverted or elongated, shifting as the air layers move. Explorers have historically reported seeing distant mountains that later proved to be much farther away, or not visible at all under normal conditions. This effect is closely related to a phenomenon called a fata morgana, a complex mirage that can create highly distorted images of distant objects. Under the right conditions, a flat stretch of ice can appear to rise into geometric shapes, with sharp edges and structured outlines. When viewed through the lens of satellite imagery or long-distance observation, these distortions can sometimes resemble artificial formations. From a scientific perspective, these are well-understood optical effects. But in practice, especially in a place where direct verification is difficult, they can contribute to interpretations that extend beyond standard explanations. And it's not just light. Sound behaves differently in Antarctica as well. Cold air, particularly when layered, can carry sound over much greater distances than warmer air. This means that noises originating far away, ice cracking, wind shifting, distant movement, can travel across the landscape and appear closer or more structured than they actually are. Researchers have recorded low-frequency vibrations beneath the ice, sometimes referred to as icequakes, which occur as glaciers shift or as pressure builds within the ice sheet. These vibrations can produce rhythmic patterns, especially when interacting with subglacial water systems. In some cases, the resulting signals have a regularity that initially seems artificial, but when analyzed, they often align with natural processes, pressure release cycles, resonance within cavities, or interactions between ice and underlying rock. Still, the experience of encountering these sounds in isolation, in a place with no other environmental noise, can be disorienting. And this brings us to another factor that is often overlooked: human perception itself. Antarctica is one of the few environments on Earth where sensory input is dramatically reduced. There are no familiar reference points, no trees, no buildings, no consistent landmarks. The landscape is uniform, and depth perception can become unreliable. Distances are difficult to judge. A mountain that appears close may be hundreds of kilometers away. A slight incline can feel like a vast slope. In these conditions, the brain begins to compensate. Patterns become more noticeable. Shapes stand out more clearly. Small irregularities in the landscape can appear significant. This is not a flaw in perception. It is an adaptation. But it does mean that observations made in such environments require careful verification. And when those observations are combined with limited data and indirect measurement, the interpretation becomes even more complex. This is particularly relevant when examining reports of unusual visual formations. There have been instances where satellite images appear to show linear alignments or angular structures beneath the ice. In many cases, further analysis revealed these to be natural features. fractures in the ice, exposed ridgelines, or shadow effects created by the angle of sunlight. But the initial images often circulated widely before those explanations were established. And once an image enters public discussion, it tends to take on a life of its own. This is not unique to Antarctica, but the continent's remoteness amplifies the effect. Because direct confirmation is rarely possible, interpretations remain open longer than they would in more accessible regions. At the same time, Antarctica's atmosphere contributes to another subtle but important phenomenon: electromagnetic variability. The continent is located near the Earth's magnetic poles, where interactions between solar radiation and the planet's magnetic field are more intense. This can lead to fluctuations in electromagnetic readings, which in turn can affect instruments and sensors. In some cases, these fluctuations can produce anomalies in data, temporary deviations that do not correspond to any known physical structure. Organizations such as European Space Agency and NASA actively monitor these effects, as they are important for both scientific research and satellite operation. Understanding how solar activity influences Earth's magnetic environment is a key area of study, and Antarctica provides a unique vantage point for observing these interactions. But once again, the presence of anomalies, even when explainable, adds to the overall sense that Antarctica operates under different rules, not different laws of physics, but different conditions. Conditions that make observation more difficult, interpretation more nuanced, and certainty harder to achieve. And this extends even to time perception. Researchers stationed in Antarctica for extended periods often report changes in how they experience time. The absence of a normal day-night cycle during certain seasons, continuous daylight in summer, continuous darkness in winter, disrupts circadian rhythms. Without regular environmental cues, the body's internal clock begins to drift. This can affect cognition, memory, and perception. It can also influence how events are recorded and interpreted. In an environment where sensory input is limited and time itself feels less defined, the line between observation and interpretation becomes more fluid. And this is why Antarctica requires a different kind of analysis. One that accounts not only for the data, but for the conditions under which that data is collected. Because the continent does not just challenge technology, it challenges perception. And as we continue, we'll begin to explore how these factors intersect with some of the more persistent theories about hidden structures and undiscovered systems beneath the ice. Not as isolated claims, but as part of a broader pattern shaped by environment, data limitations, and human interpretation. Because in Antarctica, what we see is only part of the story. The rest is shaped by how we are able, or unable, to see it. As we continue further into Antarctica's deeper layers, the discussion begins to shift from perception and interpretation towards something more structural. Not just what we think we see, but what repeated data patterns suggest might actually exist beneath the ice. Because over time, as technology has improved, certain observations have stopped being isolated and started forming clusters, patterns that appear across multiple datasets, collected years apart, using different methods. One of the most consistent of these patterns involves subglacial topography that appears far more organized than originally expected. When scientists first began mapping the bedrock beneath Antarctica using radar and seismic techniques, the assumption was that it would resemble other continental interiors, irregular, shaped by tectonic processes and erosion. And in many areas, that's exactly what was found. But in certain regions, particularly in East Antarctica, the underlying landscape appears unusually structured. Long, straight valleys, evenly spaced ridges, and in some cases, formations that maintain consistent geometric alignment over large distances. Now, there are geological explanations for this. Tectonic stretching can create linear features. Glacial erosion can carve valleys along lines of weakness in the rock. Over millions of years, these processes can produce formations that appear organized when viewed from above. But what stands out is not just the presence of these features, it's their scale and consistency across regions that have been isolated under ice for extremely long periods. And when multiple independent surveys detect similar patterns, it becomes something that researchers pay closer attention to. Another area of interest involves heat distribution beneath the ice sheet. Antarctica is not uniformly cold at its base. Certain regions exhibit higher geothermal heat flow than others. This has been measured through a combination of ice-penetrating radar, borehole data, and satellite observations. These heat anomalies influence the formation of subglacial lakes and affect how ice moves above them. But in some cases, the distribution of heat does not align perfectly with known volcanic or tectonic activity. There are zones where elevated heat flow appears without a clearly defined geological source. One explanation is that these are remnants of ancient tectonic systems, structures that no longer produce visible surface activity, but still retain residual heat. Another possibility is that the bedrock composition varies in ways that affect thermal conductivity. However, because direct sampling is limited, these explanations remain partially inferred. And this is where Antarctica continues to present challenges. Much of what we understand about the continent is based on indirect measurement. Even when multiple instruments agree on a pattern, whether it's heat distribution, density variation, or structural alignment, the underlying cause is often modeled rather than directly observed. This creates a situation where the data is reliable, but the interpretation remains open. And in that openness, certain recurring questions begin to emerge. For example, why do some subglacial lakes appear to form in clusters along linear paths? These lakes are not randomly distributed. In several regions, they align in ways that suggest underlying channels or structural guides. Scientists have proposed that these are ancient river systems, preserved beneath the ice and now filled with water due to pressure and geothermal heat. That explanation fits within current geological models, but it also raises an interesting possibility. If Antarctica once had active surface hydrology, rivers, drainage systems, interconnected basins, then the landscape beneath the ice may be far more complex than previously assumed. Not just isolated features, but entire systems that function together before being sealed. And if those systems remain intact, then what we're seeing now is only a partial reflection of a much larger structure. This idea becomes even more intriguing when we consider sediment analysis. In areas where drilling has reached bedrock or subglacial sediments, researchers have found layers that suggest periods of deposition consistent with flowing water, rather than static ice coverage. These findings support the idea that parts of Antarctica experienced dynamic surface conditions in the past. Again, this is within scientific expectation, but it reinforces the broader pattern. Antarctica is not just a frozen surface, it is a preserved system, and preserved systems tend to retain structure. Another layer to consider is gravitational mapping. Satellites equipped to measure subtle variations in Earth's gravitational field have detected anomalies across Antarctica. These anomalies indicate differences in mass distribution beneath the surface, areas where the density of material is either higher or lower than surrounding regions. Most of these variations are attributed to known geological factors, mountain ranges, sediment basins, or subglacial water. But in some cases, the boundaries of these anomalies appear sharply defined, almost as if separating distinct zones rather than blending gradually. This is not necessarily unusual in geology, but when combined with other data, heat flow, radar imaging, seismic readings, it adds to a growing picture of a continent that is internally structured in ways that are still being mapped. And mapping in Antarctica is an ongoing process. Large portions of the continent have been surveyed multiple times, each pass improving resolution and revealing new details. What was once a vague outline becomes a defined feature. What was once considered noise in the data becomes a measurable signal. And occasionally, what was once dismissed as an anomaly becomes accepted as part of the system. This has happened before. Subglacial lakes were once theoretical. Now they are mapped and studied. Ice streams were once poorly understood. Now they are recognized as key components of ice dynamics, which means that current anomalies, those patterns that don't yet fit perfectly into existing models, may follow the same path, not as evidence of something outside science, but as indicators of processes we have not fully described yet. And that distinction is important, because Antarctica does not require extraordinary explanations to be extraordinary. Its scale, its isolation, and its preserved history already make it one of the most complex environments on Earth. But complexity often looks unusual before it becomes understood. And as we continue, we'll begin to examine how some of these patterns, structural, thermal, gravitational, have been interpreted outside of scientific contexts, how they've contributed to broader theories about hidden systems, ancient activity, and the possibility that Antarctica's past may be more recent or more complex than currently accepted. Because when data repeats, even quietly, it tends to draw attention. And Antarctica, more than most places, has a way of producing patterns that invite a second look. As we move further into this layered examination of Antarctica, the conversation begins to shift toward how recurring data patterns, once identified, are interpreted beyond strictly scientific frameworks. Because while science builds models based on evidence, there is always a period where data exists before it is fully explained. And in Antarctica, that gap can be unusually wide. This is where many of the more persistent theories begin to take form. Not necessarily because the data demands extraordinary conclusions, but because the environment allows for extended uncertainty. Antarctica is one of the few places on Earth where large-scale features can remain unverified for long periods. When something unusual appears in satellite imagery or radar scans, it cannot always be immediately investigated. That delay creates a space where interpretation can expand. One of the most frequently discussed ideas involves the possibility of large-scale subglacial structures that extend beyond natural geological expectations. Some interpretations of radar data have suggested the presence of formations that appear segmented or compartmentalized, areas where density changes sharply over relatively short distances. In geological terms, this could indicate fault systems, sediment boundaries, or ancient tectonic divisions. But what makes these observations stand out is their apparent organization. In some regions, these segmented zones align with subglacial water systems, forming patterns that resemble networks rather than isolated features. Scientists typically explain this through the concept of hydrological routing, water moving along paths of least resistance, guided by pressure gradients and underlying topography. Over time, these pathways can become stable, creating consistent channels beneath the ice. However, when viewed collectively across multiple data sets, these networks can appear almost engineered in their regularity. Again, this does not imply artificial origin. Natural systems often produce structured patterns when governed by consistent physical laws. River deltas, for example, form branching networks that can look highly organized. But the scale and persistence of these Antarctic subglacial systems continue to attract attention, particularly as new mapping technologies refine their outlines. Another recurring theme involves the concept of buried surface features that predate the current ice sheet. As mentioned earlier, Antarctica has not always been fully glaciated. There have been periods, especially during warmer climatic phases, where parts of the continent may have been exposed. During those times, processes such as erosion, sediment transport, and possibly even biological activity would have shaped the landscape. What's significant is that once the ice returned, it effectively sealed those features in place. Unlike other continents, where surface processes continuously modify the landscape, Antarctica's ice acts as a preservation layer. This means that ancient surface features, valleys, basins, drainage systems, could remain largely intact beneath the ice, even after millions of years. And in some cases, radar imaging appears to support this. Researchers have identified what look like ancient river channels beneath the ice, some extending for hundreds of kilometers. These channels are now filled with ice or water, but their shapes remain consistent with fluvial erosion. This suggests that Antarctica once had active surface hydrology on a scale comparable to other continents. From a scientific standpoint, this is a logical extension of what we know about Earth's climatic history. But it also leads to broader questions. If such large-scale systems existed and were preserved, what else might have been preserved alongside them? This is where speculation begins to expand further. Some interpretations propose that if Antarctica had extended periods of ice-free conditions, it might have been accessible to early human or pre-human populations. This idea is not supported by mainstream archaeological evidence, as current timelines place human development long after Antarctica became permanently glaciated. However, the concept persists, largely because of how little direct exploration has occurred beneath the ice. And again, the key factor is not proof, but possibility. Antarctica's isolation makes it one of the few places where the absence of evidence does not immediately resolve the question. It simply reflects the difficulty of accessing the environment. At the same time, modern research continues to uncover new layers of complexity. For instance, recent studies using satellite-based gravitational measurements have revealed that the Antarctic ice sheet is losing mass at varying rates across different regions. These variations are not uniform, and in some cases, they correlate with underlying geological features. This suggests that what lies beneath the ice plays a significant role in how the ice behaves above. Organizations such as NASA have been tracking these changes closely, using missions designed to measure ice thickness and mass distribution over time. The data collected helps refine models of sea level rise and climate dynamics, but it also provides indirect insight into the structure of the continent itself. And as more data is collected, patterns continue to emerge. Some areas show consistent thinning, others remain stable, and a few even show slight increases in ice mass due to localized conditions. These variations are influenced by temperature, ocean currents, and subglacial processes, all interacting in ways that are still being studied. Which brings us back to a central idea. Antarctica is not static. It is dynamic, layered, and interconnected. And because of that, it produces data that evolves over time. What was once considered unexplained may become understood. What appears unusual may fit into a broader pattern once enough information is gathered. But until that point is reached, there will always be a period where interpretation plays a larger role. And in Antarctica, that period tends to last longer than almost anywhere else on Earth. As we continue, we'll begin to explore how historical accounts, expedition records, and early scientific observations have contributed to the modern perception of Antarctica, not just as a physical location, but as a place where the boundary between known and unknown has always been slightly blurred. Because long before satellites and radar, Antarctica was already a place that challenged understanding, and those early encounters still influence how we see it today. As we move further into Antarctica's deeper narrative, the focus begins to shift from modern data and instrumentation back to the earliest encounters humans had with the continent. Because long before satellites mapped its surface or radar revealed what lay beneath, Antarctica existed only as a hypothesis, a theoretical landmass inferred from balance rather than observation. For centuries, maps included a southern continent labeled as Terra Australis. The reasoning was not based on direct evidence, but on symmetry. Early geographers believed that the land in the northern hemisphere must be balanced by land in the south. It was a conceptual solution, not a measured one. And yet, that idea persisted long before Antarctica was ever seen. When explorers finally began reaching the southern oceans in the 18th and 19th centuries, what they encountered did not immediately confirm those early assumptions. Instead of a clear coastline or accessible land, they found barriers, ice shelves extending outward into the sea, forming walls that could not easily be crossed. One of the first to document these conditions was James Cook, who circumnavigated the Antarctic region in the 1770s. He never set foot on the continent itself, but his observations were significant. He concluded that if land did exist further south, it would be extremely difficult to reach. And for decades, that remained the case. Antarctica was not discovered in the traditional sense. It was approached, observed from a distance, and gradually understood through repeated attempts. When land was finally sighted in the early 19th century, it did not resemble anything familiar. There were no obvious entry points, no gradual transition from ocean to shore. Instead, there was ice, thick, continuous, and unyielding. This initial barrier shaped how Antarctica was perceived. Unlike other continents, which invited exploration through rivers or coastlines, Antarctica resisted entry. It required specialized equipment, extreme endurance, and a willingness to operate in conditions that were largely unpredictable. Early expeditions were not just journeys of discovery, they were experiments in survival. By the early 20th century, expeditions became more focused, more structured. Figures like Ernest Shackleton and Robert Falcon Scott attempted to reach the South Pole, navigating terrain that had no established routes. These expeditions documented not only the physical challenges, but also the psychological effects of isolation, extreme cold, and continuous daylight or darkness. What stands out in many of these accounts is the consistency of certain observations. Not anomalies in the sense of unexplained phenomena, but patterns in how the environment behaved. Navigational instruments, particularly compasses, often showed irregular readings due to proximity to the magnetic pole. Optical distortions made distances difficult to judge. Weather conditions could shift rapidly, with calm periods giving way to intense storms with little warning. These were not mysteries in the abstract. They were measurable effects of Antarctica's position and environment. But at the time, they were not fully understood. And in that gap between observation and explanation, interpretations varied. Some reports described distant landforms that could not later be located. Others noted unusual atmospheric effects that altered the appearance of the horizon. In most cases, modern analysis attributes these observations to known phenomena: mirages, magnetic variation, and extreme weather patterns. But what's important is that these early accounts established a precedent. Antarctica was a place where standard expectations did not always apply. And that perception has carried forward. Even as technology has improved and our understanding has become more precise, Antarctica retains that underlying sense of unpredictability. Not because it defies physical laws, but because it operates at the edge of conditions where those laws become more difficult to observe clearly. This is particularly evident in how data is collected. Modern expeditions rely heavily on remote sensing, automated instruments, and satellite communication. Direct human observation is still important, but it is often supplemented, or even replaced, by systems that can operate continuously in harsh conditions. These systems generate large volumes of data, which are then analyzed over time to identify patterns. And once again, patterns begin to emerge. Some align with existing models, others require adjustments to those models, and a few remain unresolved until further data becomes available. But the process is iterative. Each new data set builds on the previous one, refining our understanding of the continent. At the same time, Antarctica's history of limited access continues to influence how information is distributed. Research is often conducted by international teams operating under the framework of the Antarctic Treaty, which promotes collaboration and data sharing. However, logistical constraints mean that not all regions are studied equally. Some areas receive consistent attention, while others are only surveyed intermittently. This uneven coverage creates a situation where knowledge is concentrated in certain zones, while other areas remain less defined. And in those less defined regions, uncertainty persists, not as a flaw, but as a natural consequence of the environment. Because Antarctica is not easily mapped in full detail, its surface changes, its ice moves, and its subsurface remains largely inaccessible, which means that even with modern tools, there are still aspects of the continent that are inferred rather than directly observed. And that brings us back to a central theme. Antarctica exists at the boundary between what we can measure and what we can only estimate. It is a place where data is continuously improving, but never fully complete. And because of that, it continues to generate questions. Some of those questions are resolved through research. Others remain open, not because they are unanswerable, but because the conditions required to answer them have not yet been met. As we continue, we'll begin to look at how Antarctica fits into broader global systems, not just as an isolated continent, but as a key component in Earth's climate, geology, and even space observation networks. Because understanding Antarctica is not just about understanding what is hidden beneath it. It is about understanding how it connects to everything else. As we continue deeper, Antarctica begins to feel less like a distant, isolated continent, and more like a central component in systems that extend far beyond its borders. Because while much of the focus has been on what lies beneath the ice, Antarctica also plays a critical role in processes that connect the Earth from its core, all the way out into space. One of the most significant of these connections is atmospheric. Above Antarctica, the atmosphere behaves differently than in most other regions on Earth. The extreme cold creates a stable, stratified structure, particularly during the winter months when sunlight disappears entirely. This stability allows for the formation of the polar vortex, a large-scale circulation of air that isolates the Antarctic atmosphere from the rest of the planet. Within this vortex, temperatures can drop to levels that enable chemical reactions not commonly seen elsewhere. This is where phenomena like the ozone depletion over Antarctica were first observed. The formation of the so-called ozone hole is directly linked to these unique atmospheric conditions. Compounds such as chlorofluorocarbons, once widely used in industrial applications, accumulate in the upper atmosphere. Under Antarctic conditions, low temperatures and the presence of polar stratospheric clouds, these compounds break down and release chlorine atoms, which then react with ozone molecules. Organizations like NASA and the World Meteorological Organization have studied this process extensively, using Antarctica as a natural laboratory to understand atmospheric chemistry on a global scale. What's important here is not just the phenomenon itself, but what it reveals. Antarctica allows scientists to observe processes in isolation, conditions that are difficult to replicate elsewhere. It acts as a controlled environment at planetary scale, where variables can be studied with fewer external influences. But this extends beyond the atmosphere. Antarctica is also one of the most important locations for observing signals from space. Deep within the continent, embedded in the ice, are detectors designed to capture particles that rarely interact with matter. One of the most notable facilities is the IceCube Neutrino Observatory, which uses a cubic kilometer of clear Antarctic ice as a detection medium. Sensors are placed deep within the ice, waiting for the faint flashes of light produced when neutrinos, particles originating from distant cosmic events, interact with atoms. What makes Antarctica ideal for this is not just the ice itself, but the absence of interference. There is minimal background noise, both electromagnetic and acoustic. The ice is stable, clear, and vast. It creates conditions where extremely subtle signals can be detected with greater clarity than almost anywhere else on Earth. And sometimes, those signals are unexpected. As mentioned earlier, there have been instances where detected particles appear to originate from directions that challenge existing models. While most of these events are eventually explained within known physics, they highlight something important. Antarctica is not just a passive observer of space, it is an active detection point, a place where the Earth itself becomes part of the instrument. And this dual role, observing both inward and outward, creates a unique overlap. Because the same conditions that allow us to study the universe also allow us to study the Earth's internal processes in greater detail. Seismic sensors placed across Antarctica detect vibrations that travel through the planet. These signals can originate from earthquakes thousands of kilometers away, passing through the Earth's interior before being recorded in the Antarctic ice. By analyzing how these waves move, scientists can infer the structure of the Earth's core, mantle, and crust. In this way, Antarctica becomes a listening post, not just for space, but for the entire planet. And occasionally, it picks up signals that require closer examination. Not necessarily because they are unexplainable, but because they are rare, or because they don't fit neatly into expected patterns. For example, certain seismic readings have shown variations that suggest differences in material composition beneath the Antarctic crust. These variations could be linked to ancient geological processes, remnants of continental shifts, or localized anomalies in rock density. But again, direct confirmation is limited. Most of what we know comes from how signals behave as they pass through these regions, rather than from direct sampling. And this is a recurring theme. Antarctica provides data indirectly. It reveals patterns through interaction, through signals, through measurements taken at a distance. And while those measurements are highly accurate, they still require interpretation. Which brings us back to the idea of layered understanding, because Antarctica operates on multiple levels at once. At the surface, it is a frozen landscape shaped by wind and temperature. Beneath the surface, it is a dynamic system of ice, water, and rock. Above it, it is part of a unique atmospheric structure. And within it, it functions as a detection system for both terrestrial and cosmic signals. All of these layers interact, and all of them contribute to a picture that is still being assembled. Which means that Antarctica is not just important for what it contains, it is important for what it connects. It links climate systems, geological processes, and space-based observations into a single environment where they can be studied together. And because of that, it continues to produce insights that extend far beyond its physical boundaries. As we continue, we'll begin to look at how Antarctica is changing in the present day, not just in terms of ice loss or climate shifts, but how those changes are revealing new information about the continent itself. Because sometimes, what is uncovered is not something new, but something that has been there all along, waiting for the conditions to reveal it. As we continue, the focus begins to shift toward the present day, and how Antarctica is slowly revealing more of itself, not through direct exploration alone, but through change. Because unlike most environments where change obscures the past, in Antarctica, change can actually expose it. As ice shifts, melts, or thins in certain regions, features that have remained hidden for thousands, or even millions, of years begin to emerge. One of the most significant processes driving this is ice mass loss. Satellite missions tracking Antarctica have shown that the continent is not losing ice uniformly. Some regions, particularly in West Antarctica, are experiencing accelerated thinning, while others remain relatively stable or even gain ice due to increased snowfall. These variations are influenced by ocean temperatures, atmospheric conditions, and the structure of the land beneath the ice. What's important is that as ice recedes in specific areas, previously covered terrain becomes accessible. sometimes for the first time in recorded history. In recent years, researchers have identified exposed rock formations, ancient seabeds, and even microbial ecosystems that had been sealed beneath ice for extended periods. These discoveries are not sudden or dramatic, but they are consistent. Each one adds another piece to the understanding of what Antarctica contains beneath its surface. For example, in areas where ice shelves have collapsed or retreated, scientists have observed ecosystems that appear to function independently of sunlight. Organisms adapted to extreme cold and darkness have been found living in conditions previously thought to be inhospitable. These findings reinforce earlier discoveries from subglacial lakes, suggesting that life in Antarctica is not limited to surface conditions. But beyond biology, there is also geology. As ice thins, radar and satellite imaging become more precise. Features that were once blurred by thick ice layers can now be mapped in greater detail. This has led to the identification of additional subglacial valleys, ridges, and sediment basins, structures that help reconstruct Antarctica's past environment. In some cases, these features align with earlier models. In others, they introduce new variables. One example involves the detection of ancient coastlines beneath the ice, evidence that parts of Antarctica were once in direct contact with open water before being covered. These coastlines are identified through changes in sediment composition and topographical shifts that indicate former sea levels. What this tells us is that Antarctica's current state is not permanent. It is part of an ongoing cycle, influenced by both internal and external forces. And as those forces shift, so does what we are able to observe. Organizations like NASA and the European Space Agency have been central in tracking these changes, using satellite altimetry and gravimetric measurements to monitor ice thickness and movement over time. These datasets are updated continuously, allowing researchers to detect even subtle trends. But what makes Antarctica unique is how these changes interact with what lies beneath. In regions where ice loss is occurring, the removal of weight from the surface can lead to a process known as isostatic rebound. The land beneath the ice begins to rise slowly as pressure decreases. This movement is measured in millimeters per year, but over time, it alters the landscape in measurable ways. And as the land rises, it can reveal new information. Subglacial lakes may shift or drain. Sediment layers may become more accessible. Geological boundaries may become clearer. In a sense, Antarctica is not just revealing itself through melting, it is adjusting, responding, and reshaping how its internal systems are expressed at the surface. This dynamic interaction also affects how ice behaves moving forward. As the underlying terrain changes, it influences how ice flows above it. New pathways can form, old ones can shift, and the overall structure of the ice sheet evolves. This feedback loop between ice, water, and rock is one of the most complex aspects of Antarctic science, and it is still being studied, because even with modern tools, predicting how these systems will behave over long periods remains challenging, which brings us back to a broader idea. Antarctica is not a fixed environment. It is a system in motion, operating on timescales that are difficult to observe directly, and because of that, our understanding of it is always provisional. Each new dataset refines the picture, but it does not complete it. There are still regions where data is sparse, where models rely on assumptions, and where direct observation has not yet occurred. And in those regions, the potential for discovery remains, not necessarily in the sense of unexpected structures or unknown phenomena, but in the gradual uncovering of processes that have been operating unnoticed for extended periods. Because in Antarctica, the most significant discoveries are often not sudden. They are revealed slowly, as conditions change, as data improves, and as patterns become clearer over time. And as we continue, we'll begin to move toward the broader implications of all this. What Antarctica tells us, not just about itself, but about Earth as a whole, about climate systems, planetary history, and the limits of what we can observe in extreme environments. Because understanding Antarctica is not just about solving one mystery, it is about understanding how complex systems behave when they are pushed to their extremes. As we continue, Antarctica begins to shift from being a place we study to something that quietly reframes how we understand the entire planet. Because when you isolate a system as completely as Antarctica is isolated, you begin to see underlying processes more clearly. Processes that are always present, but usually hidden beneath layers of complexity elsewhere. One of the most important of these is time itself. Antarctica operates on timescales that are difficult to fully grasp. The ice sheet is not just thick, it is ancient. In some regions, the deepest layers of ice date back close to 1 million years. Each layer represents a specific moment in Earth's atmospheric history, preserved with a level of detail that cannot be replicated anywhere else. By analyzing isotopic compositions within these layers, scientists can reconstruct temperature fluctuations, greenhouse gas concentrations, and even volcanic activity across vast periods. This turns Antarctica into something more than a continent. It becomes a continuous record, a system where the past is not inferred from fragments, but preserved in sequence. And what that record shows is not stability, but variability. Climate has shifted repeatedly. Temperatures have risen and fallen. Ice has expanded and retreated. These changes did not happen randomly. They followed patterns influenced by orbital cycles, atmospheric composition, ocean circulation, and internal Earth processes. But what stands out is the scale of those changes. Periods of warming and cooling that span tens of thousands of years. Transitions that reshape entire continents. And Antarctica records all of it, which leads to a broader realization. The current state of the planet is not fixed. It is one point within a much larger cycle. And Antarctica provides one of the clearest windows into that cycle. At the same time, it also highlights the limits of prediction. Because while we can reconstruct past conditions with increasing accuracy, projecting future changes involves variables that are still being studied. The interactions between ice sheets, ocean currents, and atmospheric systems are complex, and small changes in one area can produce larger effects elsewhere. This is particularly evident when examining how Antarctic ice interacts with global sea levels. Large portions of the Antarctic ice sheet rest on bedrock that lies below sea level. This creates a situation where the stability of the ice is influenced not just by air temperature, but by ocean temperature as well. Warmer ocean water can move beneath ice shelves, thinning them from below. As these shelves weaken, they lose their ability to hold back the glaciers behind them, potentially accelerating ice flow into the ocean. This process is known as marine ice sheet instability. It is one of the key areas of research in climate science, and Antarctica is central to it. Organizations like National Science Foundation and international research groups continue to study these interactions, using both observational data and computational models to understand how ice sheets respond to changing conditions. But beyond the scientific implications, there is something else that Antarctica represents, a kind of baseline. Because in a world where most environments are influenced heavily by human activity, Antarctica remains relatively untouched. It is not completely isolated. Global systems still affect it, but it is less directly altered than other continents. This makes it one of the few places where large-scale natural processes can still be observed with minimal interference. And that makes it valuable, not just as a subject of study, but as a reference point, a place where we can compare what is happening elsewhere against a system that operates closer to its natural state. But even that baseline is changing, and as it changes, it reveals more about how interconnected the planet truly is. Because no part of Earth exists in isolation. Atmospheric shifts influence ocean currents. Ocean currents influence ice. Ice influences sea level. And all of these systems feed back into one another. Antarctica sits at the center of many of these interactions, quietly but significantly. And that brings us to another layer of understanding. Antarctica is not just a place of hidden structures or unexplored terrain. It is a place where systems converge, where climate, geology, and physics intersect in ways that are easier to observe precisely because of the continent's isolation. And because of that, it continues to shape how we think about Earth as a whole. But even with all of this knowledge, there are still limits. There are still regions where direct data is minimal, still processes that are modeled rather than observed, still patterns that are recognized but not fully explained. And that is not unusual, it is a reflection of scale. Antarctica is vast, and its conditions make complete observation difficult, which means that even as our understanding improves, it will likely remain incomplete. Not because it cannot be understood, but because it requires time. Time to collect data, time to refine models, time to test assumptions. And Antarctica, more than any other place, reminds us that time is an essential part of understanding, because everything there moves slowly, reveals itself gradually, and requires patience to interpret. As we continue, we'll begin to move toward the final layers of this journey, looking at how Antarctica is viewed today, not just scientifically, but culturally and conceptually, why it continues to capture attention, and why it remains one of the few places where the line between known and unknown still feels clearly present. Because sometimes the most interesting part of a place is not what it reveals, but what it still holds back. As we move closer to the final layers of this journey, Antarctica begins to shift again, not just as a physical place or even as a scientific system, but as an idea. Because beyond the data, beyond the measurements and models, Antarctica occupies a very specific space in human thought. It is one of the last places on Earth where uncertainty still feels natural, not forced, not artificial, but built into the environment itself. Most of the world has been mapped, categorized, and explained to a level where very little remains truly unknown. Even remote regions are now accessible through satellites, drones, and continuous monitoring. But Antarctica resists that completeness, not because it is unknowable, but because it operates on conditions that slow down the process of knowing. And that creates something rare, a place where questions can exist without immediate answers. Historically, Antarctica has always held that position. From the early concept of Terra Australis, imagined long before it was seen, to modern discussions about what lies beneath its ice, the continent has consistently represented the edge of understanding. Even now, with advanced technology, that edge hasn't disappeared. It has simply moved deeper. Instead of wondering what the surface looks like, we now ask what lies kilometers below it. Instead of questioning whether it exists, we question how much of it we truly understand. And that shift is important, because it shows that Antarctica's role has not diminished with increased knowledge. It has evolved. It remains a frontier, but a different kind of frontier. Not one defined by geography alone, but by the limits of observation. And those limits shape how Antarctica is perceived. In scientific communities, it is approached methodically, data collected, models refined, conclusions tested. But outside of that framework, Antarctica often becomes something else. A place where possibilities extend further, where the absence of complete data allows for broader interpretation. This is why Antarctica appears so frequently in discussions that go beyond standard science. Not because it necessarily contains extraordinary secrets, but because it allows for the idea that it might. And that distinction matters, because the perception of mystery is not always about what is hidden. It is about what is not yet fully explained. At the same time, Antarctica's isolation has led to its use as a conceptual boundary. In many ways, it represents the edge of the known world, not geographically, but practically. It is one of the few places where human presence is temporary, where infrastructure is minimal, and where survival depends entirely on preparation and support. There are no permanent cities, no independent systems that function without external supply. Everything there is brought in, maintained, and eventually removed, which creates a kind of neutrality. Antarctica does not develop in the way other regions do. It does not accumulate layers of human history in the same visible way. Instead, it preserves natural history almost exclusively, and that preservation contributes to its identity. It feels older, not because it has existed longer than other continents, but because its past is less disrupted. The layers remain, and when layers remain, they invite examination. But examination in Antarctica is always partial. Even now, with continuous monitoring, there are still vast areas where data is limited, not absent, but less detailed. Regions where mapping is broad rather than precise, where models rely on extrapolation rather than direct measurement. And in those regions, the same pattern continues. Observation leads to interpretation. Interpretation leads to hypothesis. And hypothesis remains open until further data is available. This is not a weakness in the scientific process. It is how the process works, especially in environments where access is constrained. But it does mean that Antarctica will likely remain a place where certainty develops more slowly, and where, for periods of time, multiple explanations can coexist. Some grounded firmly in established science, others extending beyond it, shaped by the absence of complete information. And over time, as more data is collected, those explanations are refined. Some are confirmed, others are replaced. But the process itself continues. Because Antarctica continues to produce new data, it continues to reveal new structures, new patterns, new interactions between systems, and each of those adds to the overall picture while also expanding it. Which brings us to a final idea. Antarctica is not just a place where mysteries exist, it is a place where the concept of mystery is sustained, not artificially, not through lack of effort, but through the nature of the environment itself. It is large, difficult to access, and constantly changing in subtle ways, and because of that, it resists complete understanding, not permanently, but continuously. As we move into the final part, we'll begin to bring all of these layers together. The scientific, the observational, the speculative, and the conceptual, not to resolve them completely, but to place them in context. Because Antarctica does not offer simple conclusions, it offers perspective, and sometimes that is more valuable than certainty. As we move toward the final stretch of this journey, Antarctica begins to settle into a different kind of understanding. Not as a collection of separate mysteries, but as a single system where each layer, ice, rock, atmosphere, and data, interacts in ways that are still being gradually uncovered. And when you step back and look at all of it together, what stands out is not just what Antarctica contains, but how it contains it. Because very few places on Earth preserve information the way Antarctica does. Most environments erase their past. Weather, erosion, biological activity, and human development continuously reshape the surface, removing older layers and replacing them with new ones. But Antarctica works differently. Its extreme cold slows nearly every process down. Ice accumulates instead of disappearing. Layers build instead of breaking apart. And as a result, the continent becomes something like a long-term storage system, one that records changes over time with unusual clarity. That storage is not limited to climate data. It includes geological structures, subglacial water systems, and even atmospheric signals that are captured and preserved within the ice. Each of these layers contributes to a broader record, one that extends far beyond what can be observed directly at the surface. And because of that, Antarctica often reveals its information indirectly, through patterns, through correlations, through signals that only make sense when viewed across multiple data sets. For example, when researchers combine radar imaging with gravitational mapping and seismic data, they begin to see how different layers align. A subglacial lake might correspond with a gravitational anomaly. A region of faster ice flow might align with a thermal hotspot beneath the surface. Individually, these observations are informative, but together, they form a more complete picture of how the system operates. And that picture is still being assembled. Because even with decades of research, Antarctica remains only partially resolved. Not due to a lack of effort, but due to scale and accessibility. The continent is vast, and much of it remains covered by ice that is kilometers thick. Drilling through that ice is time-consuming, expensive, and limited to specific locations. Remote sensing provides broader coverage, but always with a degree of interpretation, which means that Antarctica is understood in layers. Some layers are well-defined: surface conditions, atmospheric behavior, major ice flows. Others are less precise: subglacial structures, deep geological formations, localized anomalies. And between those layers, there is space. Space where models are refined. Space where new data is integrated. Space where understanding evolves. This layered approach also explains why Antarctica often appears in discussions that extend beyond standard scientific boundaries. Not because the science itself is uncertain, but because the process of building that science is ongoing. And when a system is still being mapped, still being measured, still being interpreted, it naturally invites broader consideration. But what becomes clear, especially when viewed from a distance, is that Antarctica does not require external narratives to be significant. Its complexity is already substantial. It contains one of the largest ice sheets on the planet. It influences global ocean circulation. It preserves atmospheric records that extend back hundreds of thousands of years. It hosts subglacial ecosystems that challenge assumptions about the limits of life. And it serves as a platform for observing both Earth-based and cosmic phenomena. All of this exists within a single continent, quietly, continuously, and without requiring immediate attention, which is perhaps the most unusual aspect of Antarctica. Its importance does not depend on visibility. Much of what it does, regulating climate, storing data, interacting with global systems, happens without direct observation. It operates in the background, and only when changes occur, when ice shifts, when data updates, when patterns become clearer, does it move into focus. This creates a different relationship between observation and understanding. In most environments, observation comes first, followed by interpretation. In Antarctica, interpretation often develops alongside observation, because what is observed is rarely complete. It is partial, context-dependent, and evolving, which means that conclusions are rarely final. They are updated, adjusted, and sometimes redefined as new information becomes available. And that process is ongoing, even now. Even as satellites continue to map the surface, as instruments record atmospheric changes, as researchers analyze ice cores and subglacial data, Antarctica continues to change, not dramatically, not suddenly, but steadily. And as it changes, it reveals more of itself, not all at once, but enough to refine the picture, enough to shift understanding, enough to keep the process moving. And as we move into the final part, we'll begin to bring that process to a close, not by resolving every question, but by placing Antarctica within a broader perspective. Because in the end, Antarctica is not just about what is hidden beneath the ice. It is about how we approach what we don't fully know, and what that says about how we understand the world itself. As we move into the final phase of this journey, Antarctica begins to feel less like a distant subject of study and more like a reference point for understanding limits. Not just the limits of exploration, but the limits of certainty itself. Because throughout everything we've explored, the ice cores, the subglacial lakes, the hidden mountain ranges, the signals, the anomalies, there has been a consistent pattern. We observe, we interpret, and then, slowly, we refine. But Antarctica stretches that process. It slows it down. It forces us to sit with incomplete pictures for longer than we're used to. And in doing that, it reveals something important about how knowledge actually develops. Because in most parts of the world, answers arrive quickly. Data is dense, access is easy, verification happens fast. But in Antarctica, every layer takes time. Every measurement requires effort. Every conclusion carries a degree of patience. And that changes the relationship between us and what we're trying to understand. Instead of immediate clarity, we get gradual resolution. Instead of definitive answers, we get increasingly accurate models. And over time, those models begin to converge. Not perfectly, not completely, but enough to form a stable understanding. And yet, even within that stability, Antarctica continues to hold space for uncertainty, because there are still regions that have not been directly explored, still systems that are only partially understood, still signals that require further analysis. And that's not a flaw. It's a reflection of scale. A continent this large, operating under conditions this extreme, cannot be fully resolved all at once. It reveals itself in segments, in layers, in increments, and each increment adds to the overall picture while also expanding it, which means that Antarctica is not a mystery in the traditional sense. It's not something waiting to be suddenly uncovered or solved. It's something that is continuously being understood, and that distinction matters because it shifts the focus from searching for hidden answers to observing ongoing processes, from expecting discovery to recognizing progression. And when you look at Antarctica through that lens, the entire continent begins to feel different. Not as something unknown, but as something unfolding. Slowly, consistently, and in a way that requires attention to detail, because the details are where the meaning is. The way ice flows over bedrock, the way subglacial water moves beneath pressure, the way atmospheric systems isolate and interact, the way signals, seismic, electromagnetic, cosmic, pass through and are recorded. Each of these is a piece of a larger system, and that system is not static. It evolves. Which brings us back to one of the earliest ideas we touched on, that Antarctica is not empty, it is hidden, not because something is being concealed intentionally, but because the conditions themselves limit how quickly it can be revealed. And that hidden nature creates a unique kind of space, a space where observation and interpretation coexist, where science and speculation occasionally overlap, not as opposites, but as stages in the same process. Because before something is fully understood, it often appears uncertain, and Antarctica exists almost entirely within that phase, a place where data leads, but understanding follows, and always with a delay. And that delay is what keeps it interesting, because it means that even now, even with everything we've mapped and measured, Antarctica is not finished as a subject. It is still developing, still being studied, still offering new information as conditions change and tools improve. And as we move into the final part, we'll bring all of this together, not to resolve every layer, but to place it into perspective. Because in the end, Antarctica doesn't just tell us about itself. It tells us something about how we explore, how we question, and how we understand things that are just beyond immediate reach. As we come to the end of this journey, Antarctica begins to settle into something quieter. Not as a place we've fully understood, but as a place we've learned how to approach. Because throughout everything we've explored, the ice layers preserving ancient atmospheres, the subglacial lakes isolated for millions of years, the hidden mountain ranges, the shifting signals, the evolving data, there has been one consistent thread. Antarctica does not reveal itself quickly. It unfolds, slowly, methodically, and often indirectly. And that changes how we relate to it. Because in most parts of the world, knowledge feels immediate. You look, you measure, you confirm. But here, the process stretches out. Data arrives in fragments. Observations require context. Patterns take time to emerge. And understanding becomes something that builds gradually, rather than appearing all at once. Which is why Antarctica never quite feels finished. Even now, with satellites mapping its surface and instruments probing beneath the ice, there are still layers that remain only partially defined. Not because they are unreachable forever, but because they require more time, more data, more careful interpretation. And that creates something rare. A place where the boundary between known and unknown is still clearly visible. Not in a dramatic sense, but in a steady, measurable way. You can see where the data ends, you can see where models begin, and you can feel that space in between. That space is where questions live. Not unanswered questions in the sense of something being hidden, but open questions in the sense of something still being worked through. Because Antarctica is not withholding information. It is simply operating on conditions that slow the process of revealing it. And when you step back, that becomes part of its significance. It reminds us that not everything can be understood instantly, that some systems require patience. That observation is only the first step, and interpretation takes time. And in that way, Antarctica becomes more than a continent. It becomes a kind of reference, a place that shows how complex systems behave when they are left mostly undisturbed. A place where natural processes can be observed with minimal interference. A place where the past is preserved, the present is measurable, and the future is still being modeled. All at once. And maybe that's why it continues to hold attention. Not because it hides extraordinary secrets waiting to be uncovered all at once, but because it represents something much more consistent. A slow, ongoing process of discovery. One that doesn't rely on sudden revelations, but on accumulation, on refinement, on the gradual movement from uncertainty toward understanding. And that process doesn't end here. It continues with every new data set, every new expedition, every improvement in technology, because Antarctica is still there, still shifting, still recording, still interacting with systems far beyond its surface, quietly shaping the way we understand the planet as a whole. If you've made it this far, I appreciate you being here, taking this journey all the way to the end. If you enjoyed it, you can support the channel with a like, a subscription, or by leaving a comment telling me where you're listening from tonight. It really does help grow this small corner of the internet, one thoughtful viewer at a time. But for now, there's nothing else you need to do. You don't need to hold on to every detail. You don't need to remember every concept. Just let it all settle, like layers of ice building slowly over time. Let your breathing stay steady. Let your thoughts drift. And as everything quiets down, just rest here for a moment, because Antarctica will still be there, still unfolding, still waiting, and you can always return to it whenever you need. Sleep well, and good night.